Algebra 2, Section 11.5, Geometric Series. Starting with a formula, you can see it says sum of a finite geometric series. Finite would be important. This is the formula for finite. A1 plus A2 plus A3 all the way to A sub n. The last term is A sub n. Incidentally, side note, some textbooks do use G. I can't remember if I mentioned this in another video, but lowercase g sub 1, lowercase g sub 2. I actually like that and would prefer that to make a distinction between arithmetic and geometric. But our textbook does not do that. They use A for everything, so I have been as well. But you might encounter another textbook someday that uses G. Anyway, the formula is S sub n. That would be the sum of a certain number of terms, being this n right here, right? If this is A sub 9, then you're going to have S sub 9 is equal to A sub 1, that's the first term, times 1 minus r, that's the common ratio, just like it was in section 11.3, to the n, which is the number of terms. Close parenthesis, all divided by the difference between 1 and r. Again, r is the common ratio. All of those are defined over here to the right. Okay, and we could take 10 minutes right now and really prove that formula to you. I'm sure you don't want me to do that. You'd rather just know what the formula is and how it's used. So here's an example where we'll use it. Use the formula to evaluate the series 5 plus 15 plus 45 plus 135 plus 405 plus 1215. We'll do that by doing S sub n, which is S sub 6, right? 6 numbers, is equal to the first term 5, A sub 1, times 1 minus r to the n. Well, r, how do you get r? Well, one way to do that is to say, how do you get from 5 to 15 and then 15 to 45 and then 45 to 135? That's multiplied by 3. The r value is 3. Again, I'm using the formula from the previous page. Another way to do that would be to take a current term and divide by the previous term. This is why it's called a ratio. 1215 divided by 405 is 3. 405 divided by 135 is 3. This number by this number is 3. This would give you 3. This would give you 3. That's why it's a common ratio. 3 to the n, in this case, n is 6. We already knew that. All over 1 minus 3. 1 minus r, in this case, is 1 minus 3. Okay? Now, you want to use your calculator for this. The denominator there will easily simplify to negative 2. But I am using my calculator here just to get an accurate number. And that is 1,820. That means that the sum of those 6 numbers is 1,820. And you might say, and I usually do get this question, what's the point to the formula? It would have been easier to just add the 6 numbers. And that is true enough when there's 6 numbers. But what if there were 35 numbers? You know, there becomes a point where the formula becomes more valuable than having to add up. It becomes a time saver than having to add up the numbers. And not only that, the problem said use the formula, and the the state standard says you're to learn the formula. So please, even on a simple one, even if it was 3 numbers, use the formula. And it comes out to 1,820. Now, if you add the 6 numbers up, that would be a way to check and make sure that you got the right answer. Side note, incidentally, you could model this situation with summation notation. There's 6 numbers. That means you could go n equals 1 to 6. What goes here is the explicit formula. You learned about this in section 11.4 with arithmetic. I can do the same thing with geometric. I could put the geometric explicit formula here. That's something from 11.3. Now, please let me not be confusing. In 11.4, where we did arithmetic series, we put a formula here from 11.2. Now we're in 11.5, and I'm saying we could put a formula in here for 11.3, which was geometric sequence. The sequence that generates 5, 15, 45, 135. Well, that's first term times common ratio to the n minus 1. This summation notation describes this situation exactly, and its sum is 1,820. All right, next example. The Floyd family starts saving for a vacation that is 1 year away. They start with $125. Each month they save 8% more than the previous month. How much money will they have saved 12 months later? Now, I like to put myself in the shoes of Mr. Floyd. And I sit the family down and I say, okay, family, we want to go on vacation, but right now we only have $125. But I have a plan. And we're going to start by saving 8%, and then 8% more than that each month. And then we'll see after 12 months, we'll see how much money we have. Who's with me? I'm being funny. I don't know if that's coming through on the video. Anyway, what they're asking to do here is to find the sum of 12 numbers. Now, hold on. You could argue that it's 13. In fact, I think I might argue that it's 13. But if I remember the answer that they get, right, that it's going to be 12, and I want my answer to match theirs. So there's really two ways that you could interpret this. We have 125 the first month, and then in 11 months from now, we're going to go on vacation. That's a total of 12 months of adding numbers. Or you might, I sort of read it this way. We have $125, and we have a whole year, including each of the 12 months, to do this. In any case, they're not going to do that. They're going to use 12 here. I'm arguing for it might be 13. I think it's maybe a little bit unclear on this problem. You may be looking for the 13th number and 13 numbers to add up. Anyway, I'm using 12. You could argue 13. The first term is 125. That's how much money we have now. 1 minus r to the n. Okay, the r would be the r that would go into a geometric sequence that you would multiply by, okay? Now, this could be confused with other things we've done this year in which you would just use 0.08, but no, this is going to be 1.08. Think about what the common ratio is. We're taking $125 to find the next term. We'd have to multiply that by 1.08 to give me next month's numbers. So the r value is 1.08 to the n, which is 12, all over 1 minus 1.08. And again, you're going to need your calculator for this. So pardon me while I do that on my own handheld calculator. I get $2,372.14. $2,372.14. Okay? That's how much the Floyd family can spend on vacation. Now, again, if you had interpreted it with a 13, then you're going to have a bit more to add to that. And if we were to, obviously you're not taking tests this year, but if we were to put a problem like this on a test, we would make sure that it's not confusing in the way that this problem was. So, question, if we're a family of 4, let's say, where can we go on $2,372? Maybe Cleveland, visit the Rock and Roll Hall of Fame, go to a ball game, maybe hit Cedar Point on the way home. That's probably what you can do. All right, next thing. Look here where it says when the absolute value of r is greater than or equal to 1, the series diverges, approaches no limit. When the absolute value of r is less than 1, the series converges, which means it approaches the sum. Okay, so important two words here, diverges and converges. When I think of these words, I think of like, for converge, I think of like when I watch the news and there's a perpetrator and the SWAT team is converging on the place where he is. That's how I kind of remember the difference between the two words. Diverge, I think of divert, like to send in a different direction. Okay, to diverge means it's going away, like it's going out of control. This series will never be able to get a handle on what the sum is. Converge is the opposite of that. It's actually converging toward a number, and we will be able to get a sum. I'm going to demonstrate this for you. Okay, so as an example, here are two geometric sequences. The first one does converge. Okay, and the way you know this again is by the r value. How would you get from 1 to 1/5? Forget about the plus sign for a moment and think of them just like if there's commas there and this is a geometric sequence. How would you get from 1 to 1/5 to 1 over 25? The next number would be 1 over 125, 1 over 125. Well, that's by multiplying by 1/5. The r value is 1/5. That means it's less than 1. That means it's the second situation here in the definitions of diverge and converge. It's going to converge. 4, 8, 16, et cetera, that diverges. You're never going to get that sum, right? The next number is 32. The next number is 64. This is going out of control. That's going to infinity. You're never going to get the sum, okay? So there's two examples. Now, when it comes to infinite, now that's what these are with dot, 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 it means infinite. When it comes to an infinite geometric series, if it converges, then we can get the sum, and that sum is this right here. In fact, let's do the first example on the calculator, and I'll show you what it's converging to, okay? So I'm going to go over to the calculator, and I'm going to add 1 to a half to a fourth to an eighth, and you can just watch. 1 plus 1/2 is 1.5, plus 1/4. That would be the third term, 1/4, plus 1/8, plus 1/16. Now, what is this? What does this sum seem to be getting closer to? Isn't it getting closer to 2? It's converging to 2. Now, maybe you don't believe that. Maybe you think that it's going to go past 2. Well, add 1 over 32 to it. 1.96, that's almost 1.97. It's getting closer. Maybe you add 1, maybe you add the next number, which would be 1 over 64, and that'll get you to 2. But no, it just gets us to 1.984375. And then add it to 1 over 128. And I don't know how long you're going to stick with me if I continue to do this, but basically you can continue to do this and you're going to continue to get numbers that are less than 2. Add it, I mean, that's so close. You must think, oh, it's got to be the next number, 1 over 256. Nope. The next number, 1 over, that would be 512. If you play 2048, you're familiar with these numbers, right? And I'll stop there, but it's just going to continue, and it's going to continue to be a number less than 2. And the numbers here will continue to go to 9, and the next one will be 9, and the next one will be 9, and it'll be 1.99999, but it's never going to get to 2. And if you continue to do this forever on your calculator will eventually give up and go to 2, okay? But that's not because the sum did get to 2. It's just because the rounding got so far into the decimals that your calculator couldn't handle it anymore. I'm telling you that you do this for the rest of your life. Add 1 over 1024. After add 1 over 2048. 1 over, you're never going to get to 2. It's always going to be something less than 2 because this converges. Okay. Now we already saw that it's 2. Let's prove that with the formula. Do I want to come? Yeah, I can do that. I think I missed an example, but I'll come back to that in a second. The formula would be, notice it's simpler. Notice it's really just a simpler form of this formula up here, and it is. It's just a simplified form. This is what happens when you plug infinity into this formula. And it would be simple as a sub 1, which is the first term, over 1 minus r, which is 1/2, right? To get from 1 to a half is multiply by a half. Multiply by a half, multiply by a half, the next one would be 1/16. So this is, now you need to be careful with this calculation, 1 over 1/2. 1 divided by a half. See, 1 minus a half is a half. 1 divided by 1/2 would be 2. This is converging to 2. Now, you might wonder why we didn't have a number, a subscript number here. It's because it's an infinite number. I have seen some people put an infinity there. You don't need to do that, though. Our book does not do that. If you did, I know what you're doing, but it does not need to be there. Okay, let's do a slightly more complicated one. 3 minus 3 over 2 plus 3/4 minus 3/8. That would be 1 over, I'm sorry, not 1, 3 over 1 minus the common ratio. Now again, I'll give you a minute to think about this one. What would the common ratio be? You can pause the video if you need to. How do you get from 3 to negative 3 over 2 to positive 3 over 4 to negative 3 over 2? Wouldn't that be minus negative 1/2? So minus negative means plus. And 3 divided by 1.5 then would be 2. Now it's a coincidence that both of these are 2, that both these examples are 2. It's not always that the answer is 2. And what's interesting about this second one is that, if we were to kind of plot these out on a graph, and here's 0, and this line right here is 2, 3 would start above, but then when you subtract 3 over 2, you're at 1.5, it would go below. But then when you add 3/4, it would go above. And then when you add the next one, it would go below. And they would be converging on that number like an asymptote, but they're jumping from above to below. Whereas here, if we just tracked them, and this is 2 like this, they would just track like an exponential decay function. Okay, now one other thing about that I just thought of as we go back to the finite geometric series, do be careful with the r value being negative here. I think this will happen in your homework one time. If the r value is negative, you need to raise that to the power first before you subtract. Exponents before subtraction. So what I did here, which was 1 minus negative a half, was totally legal here. That would not be, and it would be legal here in the denominator, but it would not be okay to do here, right? If it's negative 2 to the power of n, whatever n is, and get it, that number, whether it's positive or negative, it gets subtracted from 1. If it's negative, then yeah, 1 minus negative. But if it's positive, it's 1 minus the positive value of that. A negative to an even power could become positive, right? All right, now, I think that I've covered everything except I think I skipped an example here. Yes, I did. Okay, so just to finish, I'm going a little bit out of order, but you should follow, no problem. It said decide whether each infinite geometric series diverges or converges, and then determine whether the series has a sum. It doesn't say find a sum, it just says determine whether it has a sum. So here you have summation notation going from 1 to infinity, right? So that's infinite, and 2/3 to the n. This would be converge. You see, saying 2/3 to the n is like saying 1 times 2/3 to the n, and the r value is this number 2/3. And when r is less than 1, when the absolute value of r is less than 1, it's converging. And you can even think about that, like what would this produce? When n is 1, you'd have 2/3. When n is 2, you'd have 2/3 squared, or 4/9. And then you'd have 8 over 27. And those numbers are getting smaller. Therefore, they are converging. And we could actually put that into the formula too. Now, you might look at that too and say, why isn't there an n minus 1? It doesn't have to be an n minus 1. It's still a geometric sequence without the n minus 1. If it were an n minus 1, then we'd have 1, 2/3, 4/9, 8/27. That would be the only difference. And then finally, what about 2 plus 6 plus 18 plus etc.? That obviously diverges. It diverges because the next number would be bigger than 18. The next one would be bigger than that, bigger, bigger, bigger. So we're never going to get a handle on that sum. Okay? And just to answer the question, diverges or converges, then determine whether the series has a sum. Yes, this one has a sum. No, this one doesn't. It has everything to do with whether it converges or diverges. All right, thank you for tuning in.